So we are going to be talking today about chemical and physical changes and properties. And I'm going to move this thing and then it's going to switch over because it does every day. I don't know why it has to be like that, but it does. All right. So a chemical change is going to be a change that's going to form new things. A physical change, the matter will change form, but it's not going to change identity. So if we have a popsicle that melts, if we have paper that we cut up, okay, or shred, it's still going to be paper, okay? Now, if we take that paper and we burn it, it's going to be something different, okay? Remember, all phase changes are physical changes. So we talked about 6 different phase changes a couple of days ago, and all of those are going to end up being physical changes. So phase change, physical change. Because remember, we're just weakening the attractive forces between those molecules. We're not actually changing the molecules into something else. All right. Physical and chemical changes, they're going to undergo 2 types. Physical, you're not going to change the composition. Chemical, you are. So something new is going to come out of that. So rusting, burning. Most of your cooking is going to be, anytime you fry something, anytime you bake something, it's going to do that. Okay. 4 signs of a chemical change that you look for. Are they different colors? Now, that's not always the case. Like if you take a crayon or a colored pencil and you color something, that's not going to do it. If you dye something, that's not going to do it. But if you take an egg white, right, and you put that in a fry pan and it's clear, and then you heat it, it's going through a chemical change, and now you're going to have an egg white. Does that make sense? Okay. A change in temperature. So heat is released or absorbed during a reaction. Combustion, for example, when you burn something, it gets hot. Those ice packs that you have in a first aid kit where you kind of twist them and you break an inner seal and then they get cold, that's going to be a chemical reaction. You're going to change the heat. Production of a gas that's released during a reaction. So fizzing, bubbling, other than a chemical change. Now your pop, I don't know if that's pop or not, but your pop, that has a fizz in it, okay? That is just a mixture. It is a mixture of water, some sort of syrup that they put in there to give it flavor, and then they inject carbon dioxide gas. You might have like a soda stream machine, or you've seen those at people's houses before. Those are just mixing carbon dioxide in with that liquid. And over time, if you leave it uncapped, that carbon dioxide will come out of solution, and then your pop is flat. Okay. But we can get gas bubbles that form during a reaction. Production of a solid that settles out, that's called a precipitate. And I want to show you an example of a precipitate today. Okay. When you have a precipitate, and I'm going to try to see if I can change this slideshow here so that people at home can see this too. I got to go to, nope, not there. I got to go here. And then, will it let me, is this even recording? Yeah, it's recording. Yeah. You're sharing your screen. Okay, so we got a test tube. And in this test tube, I am going to put some potassium iodide. I'm going to try not to spill it. And you can see that this potassium iodide is just a clear liquid in here. Okay. I am then going to take another test tube and I'm going to fill this with some lead nitrate, which is another clear liquid. Okay, so both clear liquids. Try that again. Clear liquids. I don't know why this side is all foggy here. Didn't make it any better. And I got to go opposite direction of where I want to see it. Okay, so clear liquids. I'm going to mix these two together. Okay, when I mix them together, watch what happens. Come on out of there. There we go. Okay, so that is what that looks like when those two interact. That yellow substance in there then is a solid. That is a precipitate. And in lab, in the next couple of days, you guys are going to take and you're going to make your own precipitates, and then we're going to filter those out. And I'll show you how to do that. Okay. So that is what a precipitate is. So that you can start to see that that yellow is starting to fall to the bottom now. And if we let this sit here for a little bit, it'll continue to do that. I'll try to set these here. There we go. So that is called a precipitate. You need to add this slide. Oh, this thing is driving me nuts. You need to add this slide to your notes. So off to the side, add these items in to your notes. So matter is not created or destroyed in a chemical or physical change. In a chemical change, we just rearrange those atoms, but we don't get rid of anything. Okay? Okay, so we are going to start out with stuff in a chemical change. We're going to start out with these things in the beginning here, the lead nitrate and the potassium iodide. And I will teach you how to know what these symbols and what these names are and everything. We're going to get to that. Okay, those things are called reactants. So the stuff that you begin with is a reactant. These are the two things that I had in the test tube. I had the lead nitrate and I had the potassium iodide. When we go through a chemical change, all we're doing is rearranging stuff. Okay? So what we're doing is we're taking the lead and the iodine and we're putting those together in the chemical change. So we're going to form PbI2. And then your K and your NO3 are going to go together. Okay. And I'm going to teach you guys how to do all of this fancy symbols and how everything goes together and the subscripts that I'm switching around. All of that stuff is coming. You just got to give us time. We have to have this equation, and I'm going to show you how to balance equations coming up this year too. Okay. So that we can keep the same amount of stuff over here. So when I start out, I've got one lead here and I've got one lead here. The stuff that we end up with here is called a product. Over here, I've got two nitrates. Over here, I have two nitrates in the product side. I have two potassium here. I've got two iodine on the reactant side, and I've got two on the product side. Okay. You don't need to know how to write these formulas yet. You don't need to know how to balance the equations yet. I'm just showing you that what we start out with, our reactants, what we end with, our products, that we're going to end up with the same stuff on both sides. We just rearrange and move things around. Okay. All right. Add this to your notes. So we've got 50 grams of sodium. They're reacting with chlorine, and they form 126 grams of salt. How much chlorine did we start out with? All right, what are our two reactants?
Sodium.
Okay, so we have sodium and we have chlorine for our reactants. We know that we're starting out with 50 grams of sodium. We don't know how much chlorine we're going to have, but we know that our products are going to end up being how much?
126 grams salt.
126. If our reactants have to equal our products, how can we figure out our chlorine?
126 minus 50.
Right, 126 minus 50. Anybody got that one in their head? 76 grams. Okay. So do you see how we figured that out? If we know that our reactants equal our products, we know the mass of our products, and we know one of our reactants, the other reactant has to be the difference. Does that make sense? We figured that out? Okay. All right, properties then can be classified into two groups. Physical properties. They are ones that can be observed without changing the material. So we can take mass, we've got volume, we've got length, width, we've got density. All of those things can be done without changing the material. Chemical properties then, we have to change the material in order to observe them. Additionally, physical properties can be either intensive or extensive. Intensive properties are ones, it does not matter how much material you have. It's going to be the same amount. Okay? So the ability to burn, density, all those sorts of things. I don't like the ability to burn because that's not really a physical property. We're going to get rid of that guy. Density would be one. Let's replace that with melting point. So it doesn't matter how much you have present, as long as you can measure it. So if I have a cube of ice, its melting point is what? Either Celsius or Fahrenheit, I don't care. What temperature does ice melt at? It's wintertime. Are we going to form ice on the roads? What temperature are we worried about? 0 degrees Celsius or 32 Fahrenheit. Okay? It doesn't matter if I've got a cube of ice or a block of ice. That thing's going to melt at the same temperature. It's going to melt at 32 Fahrenheit or 0 Celsius. Okay? It's also going to freeze at the same temperature. Melting point and freezing point are the same temperature. Did you guys know that? Ice melts and freezes at the same temperature. It's just whether we're putting energy in and melting it or taking energy away and freezing it. Melting point, freezing point are the same temp. Okay, so the melting point. Density. Does it matter if I have a milligram of water or a gallon of water? What's water's density? From lab. Anybody remember? What does Craig want to be in the conference? Number 1. Yes, the density of water is 1 gram per milliliter, or 1 gram per centimeter cubed. Okay, so water's density is 1. It doesn't matter how much I have of it, it's always going to be 1. So that's an intensive property. Extensive properties, then, the amount of matter will change it. So mass, if I have an extra amount of water, the mass is going to change. If I have an extra amount of volume or extra amount of water, the volume changes. So it doesn't matter how much you've got, or it matters how much you've got. So the way you remember this is extensive properties, extra makes a difference. So extra with extensive properties, it's going to make a difference. So if I have extra material, my mass will change. If I have extra material, my volume will change. If I have extra material, my length will change. My width, my height, extra makes a difference with those. All right, so properties of matter. Can you determine the property without changing the identity? If the answer is yes, then it's a physical property. Does the property change if you have extra? If the answer is yes, it's extensive. If it's no, it's intensive. If you can't determine the property without changing the thing, then it's going to be a chemical property. My last slide. I don't have any you-dos in here. Or am I froze up? My computer freeze up on me again?
Yeah, you have 2 ideas.
There we go. Now it's better. Okay. Okay, there we go. Sometimes the thing freezes up. Density of an object is a ratio of mass to the volume. Essentially describes how tightly the things are packed. Mass and volume are extensive properties, but when we ratio those, we end up getting an intensive property. So chemical properties, how a substance reacts in the presence of air, water, acids, bases, others, chemicals, that's going to be chemical properties. If it catches on fire, so if it's combustible. Extensive properties, then extra is going to make a difference. So here's some examples for that. And then intensive properties, color, conductivity, malleability, luster, ductility. We need to talk about what some of these words mean because some of you are not familiar with them. So conductivity means, can we get electricity to flow through it? I think you guys are probably familiar with that. But malleability, you may not be as familiar with. So can we flatten it out into a thin sheet, or is it just going to be brittle and break apart? So for example, have you ever seen like where they're talking about a blacksmith and they heat up the iron and then they can take a hammer and flatten it out like into a horseshoe or different shapes? That is a property of malleability. That's how they make like your aluminum foil, for example. They get it into thin sheets. Luster, then, is how shiny something is. So typically metals are shiny. And then ductility, can we heat it up and pull it out into thin wires? So this is how they make like the copper wiring for use in electrical kind of things. Okay, so that's ductility. All right, so which of the following is a chemical change? Which one of these things will cause the paper to turn into something else? Burning it. Yep. So that is going to be your chemical change. All right, here we are looking at extensive properties. So which of these things will extra make a difference in? So if I have height, will height change if we have somebody who's taller?
Yes.
Yeah. So extra is going to make a difference here. If I have a cup of water or a gallon of water, what is its boiling point? What's the boiling point of water? Zero Celsius is where it freezes. Where is it going to boil? 100. Yep. So water is going to boil at 100 degrees Celsius. Does it matter if I have a cup of it or a gallon of it? No. So extra is not going to make a difference in boiling point. So that is not an extensive property. Now, it's going to take more heat energy to get the gallon of water to boil versus a cup of water, but it's still going to boil at that same temperature. Density. Does extra make a difference in terms of density?
Yes.
If I have a okay, you guys did density for your water, right? Do you remember doing that with the graduated cylinder and the beaker? So the 20 mils, the 40 mils, the 60 mils, did the density change, or should the density have changed? No. No, it was supposed to be 1 gram per milliliter, and you tried to get close to that. Most of you were in the 0.99 range or something like that if you did a decent job. So the extra did not make a difference with density. So that's not going to change that. And then hardness is the same way. It doesn't matter how, if I have this 1 inch thick or 5 inches thick, it's still going to be hard. Okay. It may be more brittle. I may be able to bend it more if I have less of it, but it's still going to be hard. All right, so see if you can work with the person next to you to determine these things, which would be considered a chemical change. Oh, yeah. All right, cookies baking. What do you think? Is that cookie dough going to be the same thing when it's a cookie? No. So that is a chemical change. So that is considered that. Melting. Anything melting. Melting is we talked about it on Monday. What is melting? It is it's a phase change, and all phase changes are physical changes. So that would not be one. Sugar dissolving. If that sugar dissolves and then I let that sit there for days on end and the water evaporates away, what am I going to be left with? Sugar again. So dissolving is a physical change. Stretching a rubber band. Is it still a rubber band?
Yes.
So that is a physical change. So just one of those there. Okay. All right. Categorize this as physical, chemical change or property. And if it's a physical property, is it intensive or extensive? You got 5 things there. Go. You guys were talking on the last one. Talk to your person next to you. Talk it over. See what it is.
The potential to set on fire. This one is like how the flammability, the ability to set on fire won't change with different gases. If it said like burning of paper, then that would be
All right. Volume. What is that? Can I measure volume without changing the stuff?
extensive.
Okay. Yep. It's going to be a physical property. And then once you identify it as a physical property, you got to go between intensive and extensive. Does extra make a difference in volume? Yes. So this is going to be number 4, an extensive physical property. Crushing a can. What is that? Is that gonna change it, or is that just a property?
That's a physical change.
It's a physical change because it's going to change its volume, right? How much space it's taking up when we crush it. But it's still going to be a can. So this is going to be a physical change. So this would be number 1. Freezing point. The point at which something freezes.
That was
Yep, that's a physical property. And then will extra make a difference? No, it's still going to freeze at that same point, okay, that same temperature. So that's going to be an intensive physical property. Mixing sand and water.
Physical change.
Physical change, right. We still have sand, we still have water. We could filter out that sand and have the water left behind. That is going to be a physical change. Anytime you have a mixture, mixtures are always a physical change when you create that mixture. Flammability. Are you actually catching something on fire here? No, so it's going to be a property. So then we have to figure out which property it is.
Intensive, it doesn't change.
Well, if I take this paper and I burn it,
chemical property.
is it going to change? Is it still going to be paper?
Well, I meant like with different amounts of mass, like the ability for it to be set on flame is going to be the same.
Okay, all right. So, but it's going to be chemical, though, right? Right?
Okay.
Yeah.
Okay.
Well,
so it's an
isn't
intensive chemical property, but yeah,
oh,
we don't distinguish between intensive and extensive in terms of chemical properties. It's only in terms of physical properties that we talk intensive, extensive.
you had written like in the like intensity section, that like melting point or like ability to burn.
Yeah, and I thought I changed the ability. I thought I took that out. Yeah, because I didn't like that. So that should have been redacted. So sorry. I'm changing my notes over and I'm using a different system, and the stuff that I've got, some of the stuff I'm finding I'm not happy with. So, oh, this must be leftovers. Yeah, that was just a leftover from previous. Okay, we are through the notes for this chapter. So I want to spend a little bit of time talking about your labs for this chapter and start to preview those. So I want to preview the one for Monday, and I want to preview the one for Tuesday as well. All right, so I want to show this guy here. Okay, so I'm going to hand out this lab, and then I want to talk about it with you guys. This is the lab that we're going to do on Monday. Let's see how much of it we can get through today, our discussion on it. All right, so first of all, you need to know what a crucible looks like. So this is what a crucible looks like. And this crucible, so it says obtain a crucible and lid from your teacher. There should be a lid here. I don't have it, but there's going to be a metal lid that fits on top of here. You are going to have a substance in a little cup here, and that cup, it'll get labeled between now and then. That's going to say KClO3. So here you can see that this is what that substance is. This is potassium chlorate. So when it says add approximately 1 gram of potassium chlorate will be written on here, and you'll be able to see what that formula looks like. Okay, you're going to add 1 gram of it. So the way you're going to do that is you're going to put your crucible on the balance with the lid. You need to have the lid with it. And you're going to hit what? Either tare or 0. Remember, we talked about the labs or the how to work those scales. Okay, and that tare or 0 will remove the weight of the crucible and lid, but you need to have the lid there with you. Okay, you're going to, after you've recorded that in your data table. Why is this not moving? Page down. So you've got a data table on the next side here. So you would record the crucible and lid here. And then you're going to hit 0 or tare. So you might want to put that on your lid here, or right here. After you put that in the data table, you're going to hit tare or 0, depending on which scale you're using. At that point, your balance should read all zeros. Then you're going to use a scupula. So this is what a scupula looks like. And you're going to pick it up and add it to the crucible until it reads 1 gram on the balance. Okay? And then mask the crucible cover in potassium chloride and record that in your data table. Using the Bunsen burner and clay triangle. So this is what a clay triangle looks like. Okay. The clay triangle is going to be on a ring stand. So this is your ring stand. And on your ring stand, you are going to put a iron ring. So this is what an iron ring looks like. It slides down onto this metal rod. And then you're going to place your clay triangle on that. Your crucible lid and sample then will fit down into that clay triangle, and it's going to hold it into place. You'll then get your Bunsen burner underneath here, and you're going to heat the sample for 12 minutes. So the first 6 minutes, you're going to have the flame kind of a little lower. It's still going to be, hitting the bottom of this. And then for the last 6 minutes, you're going to turn it up and get it going as hard as you can. How do we adjust our flame again? Where do we adjust it from? The gas jets. Remember, we use the gas jets to adjust our flame strength. Okay, so don't use this little dial on the side. Use the gas jet. It's a good practice to be in. Remember, if it doesn't light, you turn the barrel all the way down. You'll get a yellow flame, and then you turn it about a quarter turn, half turn, and then it'll be that blue flame that you want. You're going to need to allow this to cool. There's going to be a little white tile at your table. That white tile is what you're going to set the crucible on when you're done with it. Okay? And you need to use crucible tongs. These are what crucible tongs look like. Did we talk about these already this year? How we hold these? Okay? So crucible tongs, you're going to be holding them, and they fit nicely around your crucible. So that's why they're crucible tongs, because they actually fit properly around there. Okay? And you can move that around and so forth and so on. Okay? So read through that lab tonight, do 3, 4 tonight, and come back with any questions you might have tomorrow. Okay? And then we need to preview that next lab.